Okay, so here we are with the cliffhanger that I left you with last week. I'm actually recording this on Tuesday, so as yet only Zay has suggested a solution. Well done, Zay. The thing I missed was I wanted to work out with this. If you remember, this was me playing. I think it was Kieran, wasn't it? Sorry, Kieran. You're probably fantastic at table tennis, but let's just say that the chance I win a game is 0.7. We play 5 games, and I was trying to work out the probability that I win one of them. And I said, okay, that's a win followed by loss, 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 loss. But that's not the only way I could win one game. That's the probability that I win the first game, but I might have lost that and won the second, or I might have won the third, or I might have won the fourth, or I might have won the fifth. Now, each of those would have the same probability because each of those would involve 0.3 multiplied by itself 4 times and a 0.7 multiplied in there as well. So the answer to my question is 5 lots of that. So that's the probability that I win one game. It's 5 lots of 1 win and 4 losses, because there are 5 ways I could win a game. I could win this one, this one, this one, this one, or this one. And we can extend that to what's the probability that I win 2 games. So this time, I want to know how many ways I can pick 2 out of these 5. And it's not 2 consecutive games. It could be that one and it could be that one. How many ways can we do it? And the way we calculate it is something that you've come across before. 5C2 is the number of ways you can pick 2 from 5. That's the calculation that we've done on our calculator before. And that's the number of ways I can win 2 games. And each of those ways would have the same numbers multiplied together, albeit in a different order. They would each involve 2 wins and 3 losses. And in fact, I could rewrite this one. Instead of saying 5, I could say that's 5C1. How many ways can you win 1 out of 5 games? I don't know if this rings a bell. We've come across this sort of thing before. We came across it in the binomial expansion. And we call these sorts of situations binomial distributions. So we're talking here about a probability distribution. We've already met one special type. That was the uniform probability distribution, where all of the probabilities were the same. What we're dealing with now is the binomial probability distribution. Binomial, remember, means 2 numbers. And what we can say in this situation is that X, which is the number of games that I win, can be modelled as a binomial distribution. And it's binomial, it's 2 numbers, it's described with 2 numbers. Well, the 2 numbers are the number of games I'm playing, 5, and each time I play that game, what's the probability that I win? And this notation here is something that we're going to become very familiar with. So something can be modelled as a binomial distribution if it fits a particular sort of problem. This is taken from page 88 in the textbook, so that's the Year 1 Stats and Mechanics book, so you can have a look at that rather than trying to scribble this down now. But if we're dealing with a situation where whatever it is we're doing it a fixed number of times, if whenever we do it there are 2 possible outcomes, success, failure, or one thing happens or another thing happens, the probability of success is fixed each time, and the effect of one trial doesn't affect the result of another trial, then we can use this binomial probability distribution, this way of calculating probabilities. So let's think about my games with Kieran. Yet we were playing 5 games. Table tennis is a great example because you win or lose. Football's a bit more tricky because you have win, lose or draw. But in that case, you just have to say win or not win. But yeah, no, table tennis was fine. There were 2 possible outcomes. Fixed probability of success, yeah, I said that was 0.7, and we assume that one game doesn't affect another. Now, of course, this is a model, and like every model, the models you met in mechanics as well, they're not perfect, are they? So it is very unlikely that these last two would be true in 5 games of table tennis, because Kieran would soon realise that my backhand is the weak part of my game, so he'd be playing to my backhand. So you'd probably find that his probability of winning would improve, and you'd probably find the result of one game would affect the result of another. So it's always going to be imperfect, but it works really, really well, albeit it being a model. So let's look at 3 examples of probability situations. And my question is, are these appropriate for the binomial probability distribution? Pause at this point and see if you can decide. Okay, so A, have we got a fixed number of trials? Yes, 14 students. Are there 2 possible outcomes? Yes, you either have this blood type or you don't have this blood type. Is there a fixed probability of success? Yes, 0.15, 15% of the people have the blood. And yeah, the fact that one person has a particular blood type doesn't affect the probability of the next person. So yeah, this can be described as a binomial distribution. The number of people who we'd find with this blood type could be modelled as a binomial distribution, with 14 being the number of things that are happening. In this case, it's 14 students being tested, and each time we test, the probability of success is 0.15. Well done in B if you spotted this isn't binomial, because we haven't got a fixed number of trials. We keep going until something happens. So this is not binomial. And this one is binomial, because you are recording 15 cars and the probability of red is 12%, and we will assume that there are enough red cars so that if a red car is driven by, it doesn't mean you're less likely to get another red car. And yeah, the colour of one car doesn't affect the colour of the car behind it. You don't find that sort of red cars tend to travel in packs. So yeah, so the number of red cars we would see in this case is a binomial distribution where n is 15 and the probability of success is 0.12. So here's the start of a question you're going to be doing later. We've got the dice is biased, so the probability of landing on 6 is 0.3, and it gets rolled 15 times. State any assumptions that are required to model the number of sixes as a binomial distribution. Well, all they want you to do there is to state the 4 conditions that we've already met. So you would say that you are rolling the dice a fixed number of times. We are interested in whether we get a 6 or we don't get a 6. Each time we roll the dice, the probability of getting a 6 is the same, and the result of one roll doesn't affect the result of another roll. And then state the distribution. You would just say, right, the number of sixes is a binomial distribution, and we are rolling it 15 times, and the probability of getting a 6 is 0.3. Okay, so let's actually calculate some probabilities. So here we have 20 people, and we're interested in if they're left-handed, and the probability of left-handed people, I'm left-handed, bigger brains, but 0.15 in this case. So suggest a suitable model for the random variable, so they're just expecting to say x is a binomial distribution, 20, 0.15. Justify your choice. Well, here we go, it's the 4 things again. You are taking a fixed number of people. We're interested in whether they're left-handed or not left-handed, or left-handed or right-handed. The probability doesn't change, and the events are independent. So the probability that exactly 7 members of the sample are left-handed. So we want to know the probability that x equals 7. So we need of our 15 people, 7 of them to be left-handed. How many ways can we pick 7 from 15? Well, that's 15C7. That's the number of ways you can have 7 people from in a list of 15. 7 of them are left-handed, so that's 0.15 to the power of 7. And that means that with 15 people, 8 of them must be right-handed. So that's 0.85 to the power of 8. Now that's a lot of effort, isn't it? And I don't know if you're a fan of the Goldbergs, but if I was Barry Goldberg, I'd say, already bored. So wouldn't it be good if our calculator could do it for us? And the great news is, ta-da, yes it can. So we're going to do this calculation without this malarkey. Now I think it's always worth remembering that the probability is calculated this way, but the calculator does it all for us. So we are dealing with a binomial distribution where the number of people is 20. That's referred to as n. And the probability of success is referred to as p. Okay, so I'm going to go to statistics mode. And we've been here to calculate sort of means and everything, but I'm going to go straight to the button that says dist for distribution. And look, there it is. Binomial distribution. We do normal in year 2. Binomial distribution. Now, I have 2 ways of working out probabilities. You can work out the probability of individual values like 7, or you can work out probability of more than one value. And I always use this one, BCD, binomial cumulative distribution, even if I'm only working out one, and hopefully you'll see why. So I'm going to select BCD. Okay, so I am going to say that I'm not using data from a list, I'm entering my variables, so I'm going to select var. You may find that's already selected. If it isn't, then there we go, var. I've got the number of trials, that's n. I'm doing in this question 20 times. I'm asking 20 people if they're left-handed. And every time I do, and press Xe, the probability that they are left-handed is 0.15. So I then go up here. So in the first question, we're asked, what's the probability that 7 members are left-handed? And it was this sum that we were trying to do. So I'm going to say, for lower and upper, I'm going to put 7 for both. So this is working out the probability of all the values between 7 and 7, which is just 7. And then I press Xe. Press it twice. And that's the probability. That's what I would have got had I typed that sum in. So that is 0.0160. Now, strangely, with binomial, we work to 4 decimal places. I know everywhere else we use 3 significant figures. And the reason for that is that in the old days, when I was young, we used to have to look this up in a big set of tables. In fact, you still get those tables in the formula book. Don't need them anymore because the calculator's got them, but there we go. Okay, the next question is fewer than 2 members. So I want to know the probability that x is less than 2. Now, in these 15 people, let's think about how many left-handed people I might find. So I might have found, unlikely as it sounds, no left-handed people, or I might have found 1, or I might have found 2, or I might have found 3, or I might have found 4, all the way to 15. 15. There we go. Less than 2 is... I always like to draw a picture of these. It gets a bit more complicated than this, but that's my picture. So less than 2 means 0 or 1. It's really easy to forget the 0 with binomial, but it might be that I found no people who were left-handed. So back to my calculator, press Xe again, and I'm going to change lower to 0 and upper to 1. Remember, these probability distributions are called discrete because we're always dealing with whole numbers. You're only going to find a whole number of left-handed people in your sample of 20. So I've got 0 and 1 as my lower and upper. So now it's working out both probabilities and adding them together for me. I don't have to do that. 0.1756 rounded to 4 decimal places. Okay, so page 91 in the textbook has got 4 really good questions. Question 8, you've already done the first part, but you can carry on doing the rest. You should now be able to do all of those using what we've talked about. Obviously, you can look up the solutions yourself. And tomorrow, Friday, I will move on a little bit with this. All the best.